In this video I will show some aspects of phase locking in relation to phase noise measurements with the correlation method. The basic system architecture is like this. There is the device under test, an oscillator with good performance, and I want to measure the phase noise close to the carrier. So the first thing is to split the signal and isolate the two channels from each other with a hybrid. Then there is an attenuator at the input. It gives thermal noise in case it is set to attenuation. Then a low noise amplifier, and then an important thing, an isolation amplifier, to prevent the oscillator signal from this reference oscillator to leak backwards and come in here. Because the frequency here is very close to the signal frequency, because the quad mixer gives an audio frequency in the range of a couple of hertz, from 5 hertz up to maybe 25 or 30 hertz. So it's a very low frequency into the ADC and the computer. Now the signal processing in the computer involves a very narrow filter, and the main signal has to fit to that filter. And I'm using the same filter for both channels. That's not really necessary, but that's how the software was written once upon a time. So to do this, I have to phase lock these two oscillators to a common reference. Previously, I have been locking one to the other to make sure that both have a common average frequency. And then with a slow phase lock time constant, they are independent in the short time scale, but in the long time scale, the average frequency has to be the same. Although it was drifting up and down a little bit, but that's the same as this oscillator is also drifting a little bit up and down with time. So that is a normal phenomenon to handle in the software. I have started to use a rubidium stabilized oscillator to lock both reference oscillators to the same frequency from the rubidium oscillator. So I have built now two new phase lock circuits like this. First to divide by 16, 74HC393, and then a PLL chip, 74HC4046, phase comparator 1, and then an RC link, and then to the varicap on the 10 MHz oscillator, one or the other from the two systems. I have made a measurement using a very long time constant, 22 kiloohms, and the capacitor 0.1 farad. That gives a time constant of 2200 seconds. I will show a little bit what the results of that were. Here is the screen from the Allen graph measurement in Linrad. And you can see the curve looks a little bit peculiar, with a peak here at 200, 300, 400, 500, 600 seconds about. And that is in the green channel, which is channel 1. And we can see in the frequency as function of time that there is a oscillation. And from here to here is about 1500 seconds. And from here to here about 1000. So it varies a little bit. The channel 2 is much better. This oscillation is a stability issue in the PLL loop, but the oscillation is very slow, so it doesn't affect measurements in the time scales of, say, 50 seconds or so. Here is the phase noise measurement using the same sequence of data as in the previous Allen graph. This is from nerds101, a video I made recently. This is much better than what I had previously, with one free-running oscillator and the other oscillator locked to it. Here is a typical result from when one oscillator was locked on the other. Means channel 2 was locked on channel 1 and channel 1 was free-running. And you can see the slope of the curve at 0.05432. One is at minus 35 dBc per hertz and the other at minus 22 or something. So it's a difference of about 12 decibels. Here is the phase noise spectrum of the rubidium stabilized oscillator, the LPRO 101 from Efratom. It is clear that it is much better than the two reference oscillators in my system, channel 2 and channel 1, because it's the yellow, the correlated track, that is the rubidium oscillator. Down here, statistics is too bad, but I can assume that this is a straight line, and that means that above about 0.02 hertz or so, maybe 0.03, my reference oscillators are better than the rubidium, but below, even closer to the carrier, the rubidium is better. So I should use a time constant somewhere around here when doing the phase locking. I have changed the time constant from 2200 seconds to 10 seconds, 2.2 kiloohms and 4700 microfarads. This is to easier see what to do about stability problems. Here is Linrod in correlation mode 3. That's where I can see Allen variation and frequency versus time. And with the 10 seconds RC time constant, I can see that the oscillators are following the rubidium completely at time scales above 100 seconds, and that they are completely independent up to about 15 seconds. The frequency versus time, here, green is channel 1 and red is channel 2. And when I enter the room, I cause some little unrest on the something, maybe the oscillator under test. I will now disturb channel 2 oscillator by shorting the capacitor, making the voltage to the varicap 0 for about 10 seconds. That causes a big change in the frequency of the channel 2 oscillator. It is now outside the scale up here. So I have to reduce the vertical scale. Let's see. Now I went too far. Maybe 1 is more appropriate. And here you can see the frequency was constant for a while, and then it makes this oscillatory behavior. Actually, it doesn't look oscillatory, it's just an overshoot here. I can magnify again by changing the scale. And we can see how it nicely approaches the frequency of channel 1. Now I can look at the frequency difference. It's the difference between the red and the green trace, and also the phase angle between the two signals. The yellow, that's the frequency difference. I can change the scale to show more about it. Like that. It went down here when the frequency was fixed, and then with this overshoot, and now it is back near 0. The blue trace, that's the phase shift between the channels. At this moment it is minus 172 degrees. And I have changed the scale so it has it comes near 0. What happens here is that the phase turns 360 degrees. 1, 2, 3, 4, well, maybe 10 times or so. That is because locking is done on a fraction of the frequency. I have a divide by 16. Otherwise, it would have lost locking for this big frequency shift. Now I have done the same for the channel 1 oscillator. Shorted it for about 10 seconds. And I changed the scale, and I cannot see it yet. Well, here I can see that the channel 2 frequency jump was about 100 millihertz, while the channel 1 is 450 millihertz. So the sensitivity is very different. Channel 1 shows an oscillatory behavior. Here is while I had it shorted. Then it goes up and it goes below. And when I increase the gain, I can see that it is low, it is high, it is low, it is high. And it goes again. So this is the oscillatory behavior I've seen before for channel 1, but that was with a longer time constant. So it took much more time to see these behaviors. I have made the graph run a little faster, and I will repeat the experiment. And again, while shorted, I get this frequency. And then when I let go, there is a jump down, it goes up, and it oscillates. It's an odd behavior, but this is what I observe.
This oscillatory behavior is fairly strong, damped here, and then here it's a factor of about 10. Logarithmic decrement, I think it's called. Well, I can look more carefully, and it's the same. The magnitude here and here differs by a factor of about 10. So it takes 3 or 4 oscillations until it is locked down to about the noise level. If I look at the phases, frequency difference and phase, you can, well, it's a bit hard to see. The oscillatory, it goes over 360 degrees several times. The large frequency jumps have of course destroyed the Allen variation completely up here, but that's not what I'm interested in for the moment.
This is the frequency control circuitry. A 1 PF capacitor connected to the tuning capacitor here, and then 2 series connected varicaps, and the VCO input here, and this gives the tuning range I had of channel 2, which was the first I had made. Then I do the same for channel 1, but made a mistake and connected the 1 PF capacitor to this point, which means I had a much bigger frequency sensitivity for the VCO input. So I have corrected this, and now the oscillators are similar. I have changed the loop filter by adding this RC link, 10 kilo ohms and 0.47 farads. This resistor is an 11 position switch that can be set from 1 kilo ohm up to 2.2 meg ohms. It works as a logarithmic potentiometer. I have changed the capacitor, so it is now 470 microfarads, and I have set the resistor to 44 kilo ohms. This gives me a time constant of about 20 seconds. This capacitor works like a battery, keeping a constant voltage here, which means that the variable voltage to the varicap looks through an attenuator, 44 kilo ohms, 10 kilo ohms. This reduces the gain at the frequency where regulation happens mostly by a factor of 5, and that eliminates the overshoot problem. But this, let's call it the battery, has a time constant of 2,500 seconds. And that is about an hour. 3,600 is 1 hour. So it will keep the average voltage from this point averaged over hours, while this thing works in decades of seconds. Here is what the screen looks like. And you can see both channels follow each other quite nicely. And then there is the noise. Here is when I entered the room and removed the camera, and now I put it back. To see better, I will change the scale. And what these variations are, I cannot say for sure. Most probably it is my test oscillator that varies a little with temperature, or it could be related to the LPR101, but not very likely. But of course the 2 reference oscillator, they behave as I want them to now. So I can look at the Allen variation graph, and you can see the noise from the 2 oscillators, the wiggles here, and above about 200 seconds
they are no longer present. Then I have the pure LPRO 101 frequency in both channels. But this makes a nice straight line, which is reasonable to assume that this is my oscillator that behaves like this.
This is the experimental oscillator I have used for these measurements. Now I have instead connected another LPRO 101 rubidium stabilized oscillator.
Here is the rubidium oscillator. It's very different from what I had with my own crystal oscillator. It looks like this, and obviously these variations is the crystal oscillator. Here I have had a frequency jump in oscillator in the channel 1, and also here. So there is some stability problem, which can be seen very clearly here, while the channel 2 oscillator behaves as expected at about 40 seconds, 20, 30, 40 seconds, the rubidium takes over. To see this better, I have the same scales as I had here. 0.05 for the amplitude on the frequency scale. And I can look better. 0.01. And here it's very obvious that there is a problem in the channel 1 oscillator. And I don't know what it might be. Very hard to find probably. But under normal circumstances this is not important. Since it is in one channel only, it does not come in the correlation spectrum when I do phase noise measurements. To do this measurement, I could not use the direct conversion receiver with the sound card, because the frequency here is the same as the frequency on my reference oscillators now. So I am using the SDR-IP here. KE5FX has measured the LPRO, and he finds 10 to minus 12 at 100 seconds and 2, 3, 4 times 10 to minus 13 at 1000 seconds. So he has 10 to minus 12 at 100 seconds, that's here. It looks as it would fit this line, but statistics becomes gradually very poor at long times. I would have to wait several days to get this curve out far here. And then at 1000 seconds it was here, and the red curve is essentially the other LPRO is not off by very far. So I set the scale to see this better, and then I have hit the channel 1 oscillator gently with a hammer a couple of times, and you can see the frequency went up and it went down. And here is a green dot also. So to see better what happens, I will increase the speed of the graph by a factor of 10. It was 10 seconds per pixel. Now it is 1 second per pixel. And I will repeat the procedure with a hammer on both channels. This time something bad happened. The frequency has jumped away in both channels. First channel 1, then channel 2. So I changed the vertical scale. And here you can see channel 1 made some ugly things. Channel 2 just jumped. and I will have to wait for a long time before locking is properly gained, I think. I have restored 10 seconds per pixel, starting here. So now I have been waiting almost 2000 seconds, and they are not on the same frequency yet. It seems channel 1 made a phase jump, means the frequency was far away for a short time. So when it started to try to lock, it went the wrong direction until it reached the endpoint of the phase detector, and then the voltage came in the right direction, and now it is locking. It will take some time before they are on the same frequency again. There is still some overshoot, both on channel 1 and channel 2. Much more on channel 2. I don't know exactly why, but this excursion very far away leaves a memory in the big capacitor, probably. Anyway, I will change the vertical scale now to be able to see what will happen further on. And it seems channel 1 is less noisy than channel 2. But before, when I look here, it seems channel 1 is more noisy than channel 2. It seems I changed the frequency by clicking in this box somehow. I've tried to restore the original. I will change now the vertical scale to see better what happens here. So 10 times more gain. Obviously, there is a stability problem in my channel 1 oscillator. Here it has white noise at a fairly low level as modulation, but this is not statistically normal. Obviously, there is a stability problem in my channel 1 oscillator. The frequency changes at random here. This looks like a random thing, but suddenly this is not a random noise, it's a stability problem. And here also, and here, and this thing. I don't know what to do about this. It must be very hard to detect, because one cannot work with the box open, because then the infrasound makes a very high sound noise level. And also channel 2 makes things that don't look like random noise, but not so frequently. I have been collecting Allen deviation for 19 hours now, and it seems I have a result up to about 20 seconds here. Then statistics on the correlation becomes too bad, and I don't want to wait for that. But I can see interesting things. The channel 1 oscillator is definitely problematic. It has some instability problem that should be possible to fix. And I can see channel 2, it seems reasonable. I saved the screen after 10 hours, and it looks like this, very similar when it comes to the Allen deviation curves. It has become a little bit worse here, the green trace, but the red trace is very much the same. Well, reasonably much the same. I will replace the channel 1 oscillator by my test oscillator to see if I can get something that looks better. This did not work well. the stability of the oscillator I'm using now in channel 1, I measured it before, as you might remember, and this is the same scale as I have here. I cannot use this with a long time constant for the PLL. I have to make the PLL much faster. I have changed the PLL resistor from 44 kilo ohms to 4.4 kilo ohms. That's a factor of 10. It means that the loop is now much faster, because not only is the time constant 10 times smaller, but the gain in the PLL loop is also higher. I have the same scale as I had previously, and that I had here also. But it seems I could make the locking even a little bit faster. I changed the vertical scale now to 0.01. And you can see this behavior. So I go down from 4.4 kilo ohms to 2.2 kilo ohms. There are still problems in channel 1, this event here. And at the same time, almost, there was something in channel 2 that looks not quite right. But anyway, the gain here, 0.01 in the millihertz box, means that I should see the problems in the original channel 1 oscillator quite well with this setup I have now. So I will try to fix that oscillator before I proceed. Here I'm using the UADC4 sound card, and I have had to set a narrow filter here, which means I have filtered out the noise in the 1 second region and shorter. But what I'm interested in is what happens to the frequency. And I can see here and here there have been frequency jumps. But most of the time it looks like regular Gaussian distributed noise. And here I have entered the room and maybe change the air circulation around the unit. At the same time, I have been running also the SDR-IP, and it looks exactly the same. And what you can see, what is important here is that the green and the red trace, they follow each other perfectly well, which means what I see here is the former channel 1 oscillator. And it looked more problematic when I used it as reference oscillator, but actually the swing of the noise that didn't look random to me was only plus minus, I think it was 0.5 millihertz. And that is not far away from what I see here. It's what I have here about. And here is a drift of some kind. So after all, this doesn't look too bad. And now when I'm here and the heat from my body radiates, but more is probably that I've changed the air circulation. It goes out from the screen. And of course, with the sound card, it's exactly the same. I will allow it to run for some more time to see if I can catch any interesting events. Now it has been running overnight, total 15.5 hours, and it has become unstable, my former channel 1 oscillator. So there is something wrong with it, and I have had, this is the UADC4, and here is the SDR-IP recording, and it looks exactly the same as it should. Although the Allen variation differs a little bit. Let's see, 10 to minus 11 is here. And it's just that the graph differs. The result seems to be very much the same. At 1000 seconds, 2.0 times 10 to minus 11 2.1 times 10 to minus 11. So they are essentially the same. I should mention that the structure you see here is because in one channel, channel 1, you have this structure here. That is a spur coming from the difference frequency between my former channel 1 oscillator and 10 megahertz, the rubidium frequency. That spur is not present in the other SDR IP. Here you can see it very clearly in the sound cards. We have the 10 megahertz here, and here is the signal. And it has its overtone, and if I include it, I get this structure.
When I open the box, I find that I have used one of the Teflon insulated trimmers. I will replace that. I will also replace this trimmer by this one, which is a modified version of this one, which had a too large zero capacitance, I think, nominally 6.4 pF, but I need about half a pF or maximum 1 pF. This kind of trimmers may have a contact problem on the outer surface here. I have seen that sometime. So I replace it, even though it is a very small capacitance. The crystal thermostat has been running all the time, but the unit has been switched off for many hours, so it is room temperature. When I start it, it will drift very much initially. This is 5 seconds per pixel, and the scale is now 50 times as compared to what I will want to use when looking for possible problems in the oscillator. I will have to wait maybe an hour or so. Now 2 hours and 40 minutes have elapsed. You can see up here the frequency has drifted by about 40 millihertz, and it's still drifting. I can click here to move the frequency to the center of the scale, so I can magnify in the y-axis 0.05, for example. And this looks more or less nice. Of course, the frequency varies a bit up and down, but it seems very much like a soft Gaussian distributed noise. So phase locking should work on this. I will change the time scale from 5 seconds to 20 seconds. And then wait some more time to get a longer time sequence. It looks like I have solved the problem. I don't see frequency jumps anymore. There is only one event here. And of course, when I arrived, I'm just half a meter away from the unit. I can change the scale. 0.1,
That's a factor of 2 to be able to see here if there is some. And then the most sensitive I ever had when looking is 0.01. And then it doesn't look as nice anymore, but it seems to be a fairly regular pattern. I will put it back as the reference oscillator to see whether phase locking is going to be better now. The feedback resistor is 44 kilo ohms in both channels now. It's not as bad as it was before, but it's not so good either in channel 1, the green trace. I will save this and then make a run with a smaller resistor. Here the PLL resistors are set to 10 kilo ohm for both channels. And I can compare with what I had with 44 kilo ohms, which is this. And we can clearly see that the noisy channel 1 is a little bit better, maybe a factor of 2. And we can see that in the Allen deviation. The old result with 44 kilo ohm showed for channel 2 3.42 times 10 to minus 12. And now it says 3.14. And if I hold my finger there, we can see that it has gone down a little bit. Out here, there is a much bigger difference, and that is 1,000 seconds. But if you look at channel 1, this is the old result, and this is now. The difference is much smaller. But here, well, there is no difference at all. At this point, there is a significant difference. So, it seems this is better for both channels. And if I look at the correlation curve, this is 3 hours 51 minutes, and the previous measurement was 3 hours 48 minutes, so it's the same time. And it's obvious I should decrease these PLL resistors a little bit more and make the loop faster. What is different from before is I don't see any frequency jumps in channel 1. Here, both PLL resistors are set to 4.4 kilo ohms. And I can compare it with 10 kilo ohms. If you look here, it bends down at about 50 seconds. Means that at 100 seconds, the red channel is modulated by the noise of the rubidium oscillator, but the noise that it produces itself is attenuated. And of course it has to be the same also in channel 1, but it's more difficult to see that. Well, you see much more noise here, but when I have suppressed this noise down to this level, there is also modulation from the rubidium oscillator on the channel 1 oscillator. So the optimum settings for me to use is to have a rather bigger resistor on channel 2. 44 kilo ohms was like this, while 4.4 is here. So the difference is small up to 100 seconds. So I can set 44 kilo ohms for channel 2 and 2.2 kilo ohms for channel 1, which means I will force it to have the modulation of the rubidium oscillator. But still the channels will be uncorrelated at 100 seconds. That's 0.01 hertz, and that's as close I can go with phase noise measurements. I have changed the PLL resistors, and channel 2 has jumped very much up here, while channel 1 has gone down just a little. I changed the scale, but here is just a factor of 2 from the previous. And we can guess it will take, if you look at the slope, it should go something like that. So about 500 seconds. Well, it took more time, like this. That's about 1,600 seconds. I have now collected phase noise for 30 hours with the oscillators as I just have set them up. And what I can see here is down to about my oscillators are significantly better than the rubidium oscillator. At 0.01 hertz, the yellow trace, which is the noise of the rubidium oscillator, is about 3 decibels below the noise in channel 1. Channel 1 is the one which has a short time constant, so it has the noise of the other rubidium oscillator. And it's perfectly okay. The sum of 2 rubidium oscillators is 3 decibels above a single rubidium oscillator. Channel 2, it has the noise of the channel 2 oscillator because the time constant for locking is very long. So it doesn't contain any of the rubidium oscillator noise, but it has the noise of its own. So I can measure down to 0.01 hertz with reasonably good statistics. There is a disadvantage in that the noise is about 5 decibels higher in channel 2. It could be better to make the time constant a little bit faster, but making it too fast means that I would have the noise of the rubidium oscillator. So I don't know for sure, but anyway, I can measure easily down to 0.05 hertz with good precision, and reasonably fast probably.
I have connected my Wenzel oscillator and run it for a long time, 49 hours now. And I can see at 0.01 hertz, it looks like minus 39.5 perhaps, here. I have also been running, this is with the sound card. Here is with the SDR IP units, and here it looks like minus 40. It is not quite as steep, so I can read better here. The SDR IP for channel 2 has this extra noise, but not very close to the carrier. I can compare these things with the measurement of the rubidium oscillator, which was at minus 38. The quality, the figure of merit, is the distance from the yellow trace to the red dots here, imaginary part and real part. This is more uncertain. I will take down these numbers for future reference. The Wenzel oscillator is very sensitive to temperature variations. So it has been in this box for about a week, running all the time. And it's also very sensitive to variations on the supply voltage. So here I have capacitors. These capacitors are 0.1 farad each, and they are series connected 2 and 2 to stand the voltage. They are rated 10 volts, but I need 12.5. So the capacitance is then 3 times 0.05 farads, means 0.15, that is 150,000 microfarads. And the power supply, which is some distance away from here, this room has been closed to have a constant temperature. So there is a resistance in the cable and a very good power supply feeding it.
I have set parameters so I can see what happens further away from the carrier. This is the UADC4 in logarithmic scale. And here it is in linear frequency scale. And we can see that the noise seems to be at minus 170. And it decreases a little bit when one goes further off. I also have the SDR-IP here. This is logarithmic and it's more noisy. Here this region is useless, and here also. In linear scale it looks like this, and it is a little below minus 170. And I think this is probably more reliable because the amplitude response of the SDR-IP should be very flat around 10 megahertz. While the SDR-IP, the sound card is perhaps not quite flat, 12 hertz away from zero. The frequency is 10 megahertz plus 12.8 hertz. And that's a very low frequency for the sound card, even though I have very big coupling capacitors. But there is also a digital filter in the ADC chip. With a slightly expanded scale, I can see the noise between all the spurs. These spurs are the overtones from the audio frequency at 12.8 hertz. And I can see also in the SDR-IP fewer spurs, but worse signal-to-noise ratio.
Here is the oscillator that I want to improve, and you may have seen this in earlier videos.
It has been running for 10 hours now, far longer than necessary, so statistics are very good. I follow the usual procedure to go to linear scale and read what values I have. With very good statistics, the uncertainty is very small. So I start at 0.05 hertz here, and I can read 68.1. At larger offsets, the curve becomes more noisy, and maybe I can read at 5 hertz here. The scale is 1 decibel per division, so the uncertainty is perhaps half a dB or so.
Here is what I have seen now. It's these yellow points, and they go a little bit below the Wenzel oscillator at 5 Hz offset. The crosses that you can see below is a measurement I made on the same unit in one of the recent videos. I think it was nerds101, but it could have been the one before. I have not changed anything that I'm aware of, and this is the graph I made then, and it's these blue dots.
I will try to find out how to get back better performance, or even make it better than ever before. I was using this oscillator as the reference oscillator in channel 1, as you have seen. Then the frequency was above 10 megahertz, 6.4 hertz above. I have increased the tuning capacitor to bring it on the other side of the 10 megahertz references, and that has reduced the power from 18 dBm to 13 dBm. And the noise has improved very much, contrary to the measurement at the frequency above 10 megahertz. You can see here that the yellow trace is clearly below the uncorrelated noises, while it was at the same place before. So there is a significant improvement. I will plot this data in the usual fashion and see how it looks on the graph. Minus 72 at 0.05 hertz. And 0.7 hertz here, minus 117.3. At 1 hertz, minus 122.5. That's about 5 decibels better than at the previous measurement. At 7 hertz, I'm about here. That's minus 147. And higher I cannot see because the noise level is too high. It is a little bit better now. It's the green points I have here. They are as good as the old good measurement at frequencies above 1 hertz offset. But then it deviates. It is very much like the red dots I have here, and not the blue ones, which was a more successful measurement. The impedance into this point is 16 ohms, and this is a transformation of factor 2 of voltage, means 4 of impedance. So it means I have 4 ohms in this point. I have changed the turns ratio, removing a couple of turns here. That makes the impedance lower in this point, about 11 ohms now. And then I have tuned the unit properly. It means set this inductor for lowest possible impedance in this point, because that gives the best possible loaded Q for the crystal. And the way to tune it, look with the network analyzer and measure the Q and adjust the screw on the trimmable inductor and look what happens to the Q, and there is an optimum for a certain position. And then this capacitor should be tuned for minimum noise when there is no signal. Means connect nothing to the input and measure the signal level at the output and tune for minimum with this one. When tuning this one, the frequency should be set well away from the crystal resonance, a couple of kilohertz. What I see now is a bit unexpected. Here at 0.02 hertz, the yellow trace is far below the green and red, and the imaginary part is stronger than the real part. Usually I see the opposite, that the noise goes up when I go very close to the carrier. The level at 0.1 hertz seems to be minus 85 dB, and at 1 hertz it looks like minus 124, and this is significantly better, although it's not the best I have seen with this unit. I'm going to allow it to run for significantly more time because I want to see what happens up here. And at the meantime, I have had the SDR IP units running here, and the Allen deviation is far below, the correlated part is far below the signals themselves. This is the point where the phase locking to the rubidium oscillator is complete in both channels. A little bit more than 100 seconds. So this will also run some more time. A couple of hours later, there has been an event here, obviously. I changed scale to look better. So, opening a door somewhere, closing it, I don't know. Anyway, the noise you can see here, if I look at the difference between the two channels, it looks like this. And the difference between the channels is similar to what is correlated between the channels. And if I look here, obviously the correlated part is much smaller than the noise from channel 1 or channel 2. Normally I usually see the yellow trace very close to the lower of the two uncorrelated. The Hadamard deviation looks like this. I don't know what conclusion to draw from that. The phase noise looks more reasonable now. The low noise at very low offsets is no longer present, but signal-to-noise ratio is still insufficient. Here is Allen deviation after 28 hours. Here I have entered the room. This is the performance of the oscillator when it is not perturbed. It is 5 o'clock in the morning and it has been very quiet. The Hadamard deviation is of course a little better. You have seen the interferences from open doors and other things that have been happening during daytime. The Allen deviation you can see here at 1000 seconds. It says 2.27 times 10 to minus 11. That should be the properties of the oscillator, because here red and green are on the same place, because that is the performance of the rubidium oscillator. And at 1000 seconds that is very good. So the trace here is my test object. While at 10 seconds the rubidium oscillator is very noisy. So I have my both oscillators and they are noisier than the oscillator I'm measuring. Not much, because it differs by a factor of 2 here. And maybe that means that they are the same. I don't know, but I will see in the correlation graph. Here is the correlation graph, and I can see that it seems at 1 Hertz this differs by about 3 decibels. So it means that all 3 oscillators are the same at half an Hertz or maybe 0.1 Hertz. And there is something odd up here. The channel 2 oscillator is far more noisy than the channel 1. At times of about here 10 seconds and 0.02 Hertz. That's 50 seconds, and from here to here is 12 decibels. So it is not, I'm not sure whether this high level of imaginary part is just statistics or if it has a meaning. You can see no imaginary part is closer to the, I measure the worst case, that's so much. And if I look here, this indicates that there is some phenomenon going on here that I don't understand what it might be. Maybe it could be related to the fact that the carrier here is far from center on the filter. To be able to go down to very close to the carrier, I have set a filter shape that is not really what it should be. It should be more flat, so I could have the signal totally within. In the linear frequency scale, here with 1 decibel per division, I can read values from 0.02 Hertz, and here maybe there is a problem because the imaginary part is so strong. So I don't know what it means, but I can see at 0.05 Hertz that this oscillator, the one I'm testing, is significantly better than my reference oscillators because the separation is more than 3 decibels.
The sideband noise performance has not changed much. It is the green dots I have here. They cross the Wenzel here, that is at 0.4 Hertz. In the previous measurement, the crossing point was about here, and that is a little above 0.5 Hertz. So the difference is about 1 decibel or maybe 1.5. It's interesting, however, that my oscillator is less steep close to the carrier. It's this line, while the Wenzel is like that. But I need to move the whole thing downwards, and I have had it better before, and I don't know exactly what to do, but I will try. The power level now is 14 dBm. That's because the gain is lower. When I change the turns ratio here, I have increased the mismatch between these two amplifier stages. They are deliberately mismatched, and that is in order to get a good noise floor well away from the carrier. But I have lost gain. I have disconnected the output amplifier, this one, and now I take the output from a 4-turn winding on this core and a 50 ohm resistor in series. The result on the noise is not visible, very small differences, but the power is about 10 decibels lower. I have removed feedback, so this one is open now, and I feed the Wenzel oscillator in here with a little attenuation to get the same power level out as I had before.
Here is what I see after 34 hours and 45 minutes. At 0.01 Hertz, the curve seems to bend down. I'm not so sure this is really true. It could be a statistical problem. You can see the imaginary part is not far from the yellow line. So this is a bit uncertain. And then here the noise is very high above my system noise, so these are very reliable values. I have saved the measurement I made when it was running as an oscillator. It's here, and this is after 94 hours. It was a very long time, but I didn't go as low as 0.01 Hertz that time. But the scale is exactly the same. I can mark, let's say here, 1 Hertz minus 120. That's the tip of the pencil. And then I go back to the latest. And you see it is very close. And the value is the same also. But if I look, for example, here, there is a fairly large difference. This is when my oscillator is running. And here it is an amplifier amplifying the Wenzel oscillator. And if I look up here, here is my oscillator running, and it's a little bit lower. This is 5 Hertz, and it's this point. And 5 Hertz, it's here, and here it is a bit higher. Well, I have plotted this on a piece of paper where it is easier to see what this means, because it's not so obvious from this direct comparison. It's obvious that this is a straight line, and this is curved in some funny way. The red circles here, these are the Wenzel oscillator when it's running directly into the test system. The black circles with the dots, these are the new measurements I made, and these look a little bit peculiar, but when the statistics becomes better at higher offsets from the carrier, the new data points follow the Wenzel very closely. It seems this Wenzel and that Wenzel were a little bit off, and then when we come at about 3 Hertz, then the filter characteristic of the crystal starts to improve and filter out and some of the noise from the Wenzel. And the cause of the peculiar shape is I was measuring the difference between those black circles and these green marks, which are my oscillator when it's running as an oscillator. So what I can see now is the amplifier does not add significant amounts of noise. So the noise contribution must be much smaller than the noise that comes from the Wenzel. If they were equal, I would see a 3 dB degradation, and what I see is less than 1 dB, I would think. Statistics is a little bit difficult in these things. I have added 10 decibels of attenuation between the Wenzel oscillator and my selective amplifier. And I have also increased the sensitivity of the 2-channel receiver. And here is the result. And what I had without that attenuators is like here. The difference is extremely small. At 1 Hertz I can see the yellow trace here is at minus 120 decibels. The new result, well, I have to move a little. It's here, it is minus 120 decibels. So there isn't any difference, except up here, very close to the carrier. But, as you can see, the red dots, the imaginary part, is of the same magnitude as the real part. So, and it's the same here, the imaginary part and the real part. The uncorrelated for channel 1 and channel 2. They are very similar. So, what did I learn from this? Well, nothing. You can see here, for example, the uncorrelated spectra in the old measurement and in the new. Everything is the same, except the signal level. The amplitude margin now is 2.4 decibels, but in the previous measurement here it was 4.3 decibels. That's a difference of about 2 decibels. Means the signal was compressed here to give a larger margin, but the addition of a 10 dB attenuator between the Wenzel and the amplifier was compensated by my removal of 10 decibels attenuation in the receiver. So had been no compression, I should have seen the same amplitude margin here. And I think the reason for amplitude compression at the full signal level is that then these diodes are conducting, meaning that I have this extra resistor loading this output, and that would reduce the power I can cut out from this point. I did not find anything while using my amplifier as an amplifier for the Wenzel. So now I am doing another test. Here is the selective amplifier, and I have the Wenzel and a stepped attenuator to set the appropriate signal level for the unit, and a hybrid that split the signal in two. So one goes in my two-channel receiver directly, and the other goes through my selective amplifier. And I have changed the two-channel receiver, so both channels now have the same local oscillator. Here is what I see. The yellow curve, that's the difference frequency between the two channels. And as should, it is 0. It has very little noise on it. The red trace is the frequency frequency difference between the Wenzel oscillator and my reference oscillator. And it goes up and down, but it keeps close to a constant frequency. The Wenzel oscillator is well isolated from temperature and voltage variations. The blue trace is the phase angle that I measure between input and output. And it doesn't correlate to the frequency. So it is caused by something else, and that is of course causing phase noise. And the time scale, it is 100 seconds per division, from here to here. And then suddenly something dramatic happens here. That's when I entered the room for a short time and then went away again. And I have to reduce the sensitivity. It is now 5000. I make it 500 instead for the phase. And then you can see very clearly something happened and the phase is drifting away slowly. But that isn't causing oscillations of the kind that I saw in this section. It's a frequency drift that is slow. So I will leave this running for a while and then come back. Now several hours have passed, and I don't see much similarity between the frequency variations of the Wenzel, because there should be no frequency variations, or at least very small ones, from my reference oscillator, because that is locked to a rubidium source. So I just wonder what these fairly rapid variations of the phase can be caused by presumably something electronic. I don't think the temperature can vary like this so rapidly. I just entered the room. I expect to see something fairly soon here. Well, not much has happened. Maybe I closed the door the previous time. I don't remember that. The door is closed now and has been since I started this measurement anyway. I can investigate this for various phenomena. For example, I can change the signal level by 1 decibel. The signal is now 1 decibel stronger. And you can see nothing happens to the frequency of the Wenzel, of course, but the blue trace is up here. I have to reduce the gain. I take 100 times from 5,000 to 50. And so then I want to know how much is this in degrees. I read now minus 152 degrees, and I change back by 1 decibel. And as expected, you can see the blue trace is back at 0. So now I have minus 149. Was it 152 the previous time? I have to check. I have changed by 1 decibel in the opposite direction. And it comes down here, says minus 36, and here it says plus 4. So, and now I have minus 146. This means that 6 degrees is 0.75 on this scale when I have the gain set to 50. For some reason, the apparent frequency difference between the two channels has changed. Now frequency and phase is closely related, so actually this is just a phase change through the device under test. But I can look now on the blue trace. I have to change the scale. The blue trace is at 0.25 on the scale, and since I changed gain by a factor of 10, that is 0.025. That means that I have produced a phase shift of, what did I arrive at? 0.2 degrees. And the supply voltage, it was 16.0817, and now it is 16.1812. So that is 0.1 volts. 0.1 volt gives me then 0.2 degrees. I have reduced the signal level by 10 decibels, and it seems to me that the phase is a little bit calmer now. the phase shift through the amplifier. It's the blue trace here. I will go back till full signal level to compare again. This is full power again. And here I think this blue trace, the phase difference from input to output on the amplifier, looks more noisy than it did here with a lower power level. And here is the old result at the higher power level. And it's not really perfectly clear, but I have a feeling this is something that has some meaning. I have disconnected the selective amplifier and replaced it with a BNC female to female adapter. The phase variations, the blue trace, does not have so high amplitude in these fairly high frequency variations as it had before. Here is what I saw at the reduced power level, and it's not very different. Or maybe it isn't different at all. But at full power, I think it was more of these kinds of... But my equipment isn't really good enough to study this. There are amplifiers in the two-channel receiver, both on the oscillator side and on the RF side. And there are frequency mixers and other things. And all have a phase shift, and it varies with temperature. Here I can think this is temperature. I have disconnected this amplifier also, like this. So I'm loading with the 16 ohm resistor and the 50 ohm output. So my system doesn't see 50 ohm source impedance, but it doesn't matter anymore, because I'm not using the impedance for anything. There is no hybrid anymore. The immediate result is a little bit surprising. It looks flat and not very noisy. I have to wait for a longer time. Well, it doesn't look so good anymore. So this is with just one amplifier stage, the first one. And here was the low level, and here was the high level from before. I can use this tinyPFA to measure the phase shift between these two inputs. And I have clicked on null phase, and now the phase shift is very small. I can change the supply voltage by 0.1 volt as I did before, and then it takes a little time until it stabilizes. Well, 24 picoseconds. Well, the voltage goes up slowly because I have very big capacitors and a resistor to filter out noise from the power supply. So more like 27 picoseconds for 0.1 volt. 27 picoseconds for a 0.1 volt step on the power supply. Well, one turn is 360 degrees, and at 10 megahertz that is 100 nanoseconds. So 0.097 degrees for 0.01 volts. That's 1 degree per volt. And I found recently 2 degrees per volt when I used my Linrad system. So I will have to look in the code for a factor of 2 somewhere. But for this time it doesn't matter. I have made a couple of measurements on my selective amplifier, and also with the female BNC adapter. So the green traces is when there is no amplifier, just the adapter, and it is obviously calmer than the other traces. And then the red and brown, this one and these, they are with the amplifier, both amplifiers and the limiter in the limiting mode. And the blue traces are with only the first amplifier. At this time, I changed the power supply by 0.01 volt. And then I did the same 0.01 volt, but with two amplifiers, the full configuration. And you can see that the phase shift due to the second amplifier stage is much larger. And I can evaluate it. Here it is 6.3 times 10 to minus 12. And here it is 3.5 times 10 to minus 12. The difference is close to 3 picoseconds. And that is in a good agreement with the 27 I found for a 10 times bigger voltage step. And I can see that the 10 millivolt step here is about 10 times bigger than the noise I have. The higher frequency components here. And the temperature, I associate this with temperature changes, the slower, over hundreds of seconds. The noise here then corresponds to about 1 millivolt if it would be caused by voltage variations on the power supply. Now my DC voltmeter tells me that the power supply is more stable than that. So it is noise from the crystal or from the amplifier or from connectors or cables or something. I will try to optimize this setup and then trying to find out exactly what is the origin of the phase noise I see through the amplifier. Because phase noise means changes of the phase through the oscillator, and the oscillation frequency is where the phase is 0. So if the frequency where the phase shift is 0 varies, I will have phase modulation, phase noise.